Hello and welcome to today's lesson on Newton's first law of motion. Our learning objectives are to apply Newton's first law to explain the motion of an object moving with uniform velocity, apply Newton's first law to explain the motion of an object when the speed and/or direction changes, and explain that inertia is a measurement of how difficult it is to change the velocity of an object. We'll start off with a true story about an astronaut who was out on a spacewalk when he spotted something unusual. Behind him, he saw a light flashing, and this light was flashing, and the object, whatever it was following the spaceship with its same velocity and same direction. The astronaut couldn't explain what it was. You might think that this could be some kind of strange alien craft following the astronaut around in space. In reality, the answer was much more mundane than that. A spanner had been dropped earlier on the spacewalk, and it had fallen off the spaceship and flown out into space. But because it has the same velocity as the spaceship initially, it is carried on with that velocity through space. So it followed the spaceship, spinning, and every time it spun round, it would reflect the lights back from the spaceship, creating this flashing light effect. The point here is that, at least in space, objects continue to move with the same velocity and in the same direction unless a force acts on them. Now I'd like you to imagine yourself sat on an aeroplane with your eyes closed. Now you can probably feel the vibrations from the engines as they spin around, but could you actually tell if the aeroplane was moving forwards or not? If the aeroplane is accelerating, speeding up, slowing down, or changing its direction, then we can feel the resultant force on our bodies. But if the aeroplane is travelling in straight and level flight at the same speed, then there's no overall resultant force on us, and so we can't actually detect any motion. If you're in a car going round a corner or in a theme park ride that's spinning you round in a circle, you will feel a force, and that force is pushing in on you towards the centre of that circle. It's called centripetal force. It can actually feel like you're being thrown out to the side. In reality, you're carrying on in the same direction, and it's the car or theme park ride that's moving around. And as a result, it has to exert a force on you to make you follow it around in the circle. As you can see here in the diagram, the car is moving in a straight line and then has to turn to the right. You will continue to try and move in a straight line until the car exerts a force on you to pull you around the corner. This is all explained by Newton's first law of motion. An object will continue to stay at rest or move with a uniform velocity unless a force acts on it. Pause the video here and copy that down in your books. An example of Newton's first law in action is when a magician uses the tablecloth trick. By pulling really quickly on the tablecloth, he can whip it away whilst leaving everything else that was on the table in place. This is because a large force is applied to the tablecloth, causing it to accelerate away, but the friction force between the tablecloth and the objects on the table is so small that it's not enough to get them to accelerate away, and so they pretty much stay where they were. I don't recommend you try this at home, but one thing you can try at home is this. All you need to do is place a small coin on a playing card on top of a cup or mug, and then, ideally using a ruler, tap the card and cause the card to go flying off to the side and the coin to fall into the mug. Why? Well, the card has a large force applied to it from the ruler, causing it to move off to the side, but the friction between the card and the coin is so small that the coin doesn't actually have enough force to start it accelerating, and so it stays where it is. Unfortunately, there's not a card supporting it, so it falls downwards. It may seem strange that something can continue to move without a force acting on it. We often forget about friction, which tends to slow things down and stop them. But if the speed and direction of an object doesn't change, then the overall resultant force on that object is zero. This could be because there are no forces acting on the object at all, such as the Voyager 1 probe, which doesn't need its engines to keep moving and has travelled over 20 billion kilometres. Here we have a free body diagram for a ball that's falling through the air. Name forces A and B in your book and pause the video while you do that. So force A would be drag or air resistance or possibly fluid resistance, and B would be weight or force due to gravity. And would the resultant force on the ball be 0 or not 0? Here, clearly the weight of the ball is larger than the air resistance, and therefore it would be a non-zero force, causing it to accelerate downwards. Here we have a book being pressed downwards into a desk. See if you can name forces C, D and E in your book. Pause the video while you do that. So force C would be the normal contact force or reaction force. Force D would be the weight of the book, and force E would be the normal contact force. Now for this book, do you think the total resultant force would be 0 or not 0? It's worth bearing in mind that the arrows here are not drawn to scale. And here we'd expect the resultant force to be 0, as all the forces would balance out. If the forces were shown to scale, then forces D and E should add up to the same size as force C. And for the aeroplane shown below, name the forces F and G. Pause the video while you record their names in your book. Force F would be drag or air resistance, and force G would be the weight, or again the gravitational force. If the aircraft is travelling along the runway at a constant speed, and bearing in mind that the arrows are not necessarily drawn to scale, would the resultant force on this aircraft be 0 or not 0? Pause the video while you answer the question. If the aircraft is travelling at a constant speed and in a constant direction, then the resultant force will be 0. Here we have Olympic hopeful Sky Brown on a skateboard on top of a bus. I'd now like you to pause the video and copy and complete this paragraph to explain what happens as the bus starts and stops moving with Sky Brown skateboarding on the top of it. Use the words at the bottom to fill in the gaps. And the answer would be, when the bus moves forward, the girl will move backwards. That's relative to the bus. It will seem like she's moving backwards because the bus moves forwards, as the force provided by the ground and the bus is greater than the force of friction between the skateboard and the roof of the bus. When the bus stops accelerating, the net force on the girl will be 0. If the bus brakes suddenly, it will slow down or decelerate, and the girl will continue to move forward due to inertia. Well, that brings us to the end of today's lesson. I hope you found it useful, and thank you very much.